In today's session, I am going to first discuss little bit about the GATE syllabus, then the entire course structure of the first part, that is transformer. Later on, I will also show you the books and authors which may help you in your preparation. By solving their solved example, you will be feel more good about this subject. Then transformer and its uses. Today I am going to discuss types of transformer, some basic magnetic circuit that already you have known about that. And then right hand curl rule, most important. The entire electrical machine is based on the right hand curl rule. This rule is going to be used in every part of the machine. Okay. Next, we will move towards the Faraday's law of electromagnetic induction. I am hoping that you are aware with the term d phi by dt. So I am going to make this particular Faraday's law of electromagnetic induction to be field to you. Then later on we move towards the Lenz law, and also we learn how to mark the polarity as per the Lenz law. So GATE syllabus, as per the syllabus, the topics mentions are equivalent circuit, phasor diagram, and open circuit and short circuit test. They are very smart. They have just represented a very small words in the syllabus, but that covers the entire transformer. When I am writing electrical circuit, it means automatically it includes all aspects of the transformer, theoretical and numerical. Okay. Then in the testing, they have only mentioned the open circuit test and short circuit test, but polarity test is also essential. So we will learn about the polarity test and also Sumner's test. Okay. Later on, three-phase transformer in the syllabus mentions as connections and vector groups. If you see, the word connections and vector groups automatically includes all types of three-phase transformer along with the special connections like your Scott connection as well as your open delta connection, zigzag connection. So it includes all connections. Later on, parallel operation is also mentioned, and auto transformer is mentioned in your GATE syllabus. Now please see the course structure that I am going to move through this entire your class. Okay. Introduction, today's class itself, where we are going to learn about the magnetic circuit, then ideal transformer, impedance transformation, then practical transformer, phasor diagram, and numerical sessions based on the practical transformer and electrical model. Later on, testing of transformer, per unit system and testing of transformer, transformer losses, in which we are going to learn about the core loss in very detail. Later on, voltage regulation and transformer efficiency. I have also kept a mixed numerical session so that number of numericals are going to be practiced in this course module. Further, auto transformer and multi-winding transformer, three-phase transformer after numericals based on the auto transformer, three-phase transformer connections, in which we have learned how the connections are going to be made and why that particular connection is needed. Further, numericals based on the three-phase transformer. I have created two different classes for the numerical session. Then open delta and Scott connection. We also learn about the concept of harmonics in the transformer, because that is also a very important part in order to understand different connections of the transformer. Further, numericals based on the harmonic, small just an introduction part of the zigzag connection, and parallel operation. Parallel operation is very important this year, because from last 2 or 3 years they are not asking any question from the parallel operation. So that parallel operation part is very important. Further, numerical based on the parallel operation. In upcoming classes, I am also going to discuss about the transformer as a magnetically coupled circuit, effect of magnetic coupling and also magnetic coupling concept, inrush of magnetizing current. So most of the students are confused with the main thing, that is whether induced EMF is 90-degree leading or 90-degree lagging. That concept is going to be covered in very detail in the part of inrush of magnetizing current. Okay. And a little bit about the transformer construction. It is not properly mentioned in the syllabus, but sometimes it will be helpful for the different public sector exams. And at last, I'm also going to give you our short notes in the format of formula revision. So this short notes part is going to help you to solve the number of numericals. Okay. Now, books and authors. Please observe, the most important book is P.S. Bhimrao. It is not needed that you need to buy this book. Okay. You don't need to buy this book. If you have this book, it will going to help you, especially your static part and a dynamic part. So this book is very good for transformer numericals. Only you have to solve the numericals. Okay. Only you have to solve the solved numericals. And if you want to explore the concept a little bit in more detail apart from your notes, then you can go with this book. Okay. So transformer and induction, transformer and synchronous part is described in this book in a fabulous method. This is Electrical Machinery by P.S. Bhimrao. If you want to learn a three-phase transformer and harmonic concept, more numericals based on the unbalanced three-phase transformer, then you can follow Generalized Theory of Electrical Machinery by P.S. Bhimrao. That is the second part of this. Okay. Next is, if you have this book, then that book is also very good. That is D.P. Agnihotri, D.P. Kothari and I.J. Nagrath. In this book, DC part is quite good. I found the DC part to be very good in this book. Okay. So you can go by the DC part, and also transformer solved numericals are good in this book. Okay. Next is basic book. Maybe sometimes a student will have this book because they follow this book because the thickness of this book is very small. So you can also, if you have this book, then that book is also sufficient. You don't need to buy any other book. You can just go through the objective numericals. One more book in your college, I think this book is also available in your lab. That is volume 2 of B.L. Thareja. So B.L. Thareja book is also good for the number of numericals. One book is my favorite book. This is my favorite book. I love this author. I love this book because this book gives a great information based on the three-phase induction machine and synchronous machine. If you want to learn some more machine controls with the help of power electronics, then also this book is quite good. This book is great book if you are preparing for engineering services examination also along with your GATE. Okay. So the name is Theodore Wildey. Hoping it is clearly visible to you. Great, sir. So I think up to that part is sufficient. This much of books requirement is sufficient for you. Now let's talk about the transformer. Let's talk about the transformer. I am going to discuss little bit for transformer. I am going to write everything by my hand except that part which I need to dictate. So whenever I dictate, that part is only printed here. All other things are I am going to draw it by my hand only. Okay, so that it will be easy for you to write on your notebook. Okay, now please see. Sir, why we need a transformer? The first question comes in mind. Why we need transformer? What is so important? What is so important in transformer that we have to study transformer? We have to know the complete information related to transformer. Now please see. Suppose I have a generating station. So when we talk about a generating station, then it's a prime generating station. Prime generating station means like hydropower, your base power plants. Base power plants are hydro, nuclear or thermal. And we are using a synchronous generators because synchronous generators are the prime source of all electrical energy we consume. Prime source of all electrical energy we consume. And why only synchronous generators? Because synchronous generator has only capacity to generate active as well as reactive power. We have to operate our induction machines, which are the major electrical loads in our entire distribution system. So when we talk about induction machines, they need magnetic power to build up a magnetic field. It means they need reactive power. And reactive powers can be generated with the help of synchronous generator along with the active power. So synchronous generators are the prime source of all electrical energy we consume. Now please observe, let us suppose I have a synchronous generator. Whenever you have to write anything, I will let you know. Please observe here. Suppose we have a synchronous generator. Suppose we have a synchronous generator. This is a three-phase synchronous generator I am representing. Okay. And I'm going to rotate it with the help of some prime mover. I'm going to rotate it with the help of some prime mover. Please observe here. Please observe here. Now see, suppose we have a prime mover. With the help of prime mover, I am going to rotate this generator, okay, at synchronous speed. So what happens, sir? It will generate a voltage. Yes, sir. A AC voltage will be generated by this. Great, sir. Now, when we talk about base plant, then base plants are hydro or thermal power plants. These needs a lot of amount of water. So when we have to collect a water, then it will be quite easy if we built a dam. When we are going to build a dam, then definitely if two natural boundaries are available, then only we need to put one boundary. If we are able to construct one boundary, it means automatically we can easily store the maximum amount of water, which is going to be used for our thermal as well as for the hydro. Okay. Now please observe, I have a synchronous generator, and let us suppose this synchronous generator is generating voltage at 11 kV. Okay. And the generator KVA rating is suppose 200 MVA. Okay. Now please observe. Now you can say, sir, this generator generates 11 kV voltage and 200 MVA apparent power. So it means the amount of current, that is phase current, the amount of phase current will be equals to KVA upon root 3 times of line voltage. Okay, yes sir. So KVA is 200 by root 3 into 11, and since it is MVA, so I am writing here 10 to the power 6 and 10 to the power 3. Can you calculate this? Please calculate this. It is nearly equals to 10.49 kilo amperes. Approximately 10.49 kilo amperes. So our base plant is existing in those areas where natural boundaries are available. It's a mountains. Only we need to construct one boundary. And our base load is in the plain areas. Like suppose I am generating in Tihri Dam and I am going to distribute to the Delhi. The power going to be distributed to Delhi. So the distance is quite high. Yes, sir. The current rating is 10.49 kilo ampere. Now, this current rating needs a very thick wire. Yes, sir. Whenever we talk about the thickness of wire, then thickness of wire depends upon the current rating. For low voltage devices, like if we talk about your normal tube light, then a normal tube light can be supplied by a very thin wire, usually 1 mm wire or 0.5 mm wire. You can't use same wire for supplying AC. Yes, sir. Why you can't use the same wire for AC? Sir, if we talk about a resistance of a wire, then resistance of a wire is rho L by A. Yes, sir. We can easily observe here, if the area of cross section is lower, it means resistance is high. Yes, sir. So if the area of cross section of wire is lower, then resistance is high. And if I am going to flow a high current through that wire, what happens, sir? I square R loss happened. And that occurs in the format of heat. Yes, sir. So what happens, sir? Heat increases. We all know about the behavior of the resistance. When temperature increases, resistance further increases. With the increase in resistance, what happened? Sir, I square R loss further increases. So this cumulative process goes on till wire reaches to its melting point. Yes, sir. So it means whenever we talk about the current, it can be directly related to the thickness of wire. If the thickness of wire is more, it can handle more current. If the thickness of wire is small, it can handle a low current. Is it okay? For a same material, whether you are talking about aluminum or you are talking about a copper, then you can say, sir, it totally depends upon the thickness, how much current is going to be flow through the wire satisfactorily. When that much amount of current is needed, we all know about the thickness of a AC wire. When that much amount of current is needed to be flow, then the thickness of wire is needed more than, sir, more than the thickness of Varun, sir. Yes, of course. It will be quite difficult to hang these wires onto the overhead lines. It will be difficult to hang, and also the material requirement is very high, sir. Material requirement is very high, sir. So it is not possible to make a transmission from base plant to the load end. Yes, sir. Because two different challenges. First one is, sir, material requirement is very high. Are you getting me? Yes, sir. So material requirement is very high, and also it will be difficult to hang onto the overhead lines. Yes, sir. So we found a solution. What is the solution? Sir, we can use a transformer. If we are going to use a transformer, it can increase the voltage level. From 11 kV, we can increase the voltage level to 440 kV. Is it okay? Yes, sir. So if I am going to increase the voltage level, what happens, sir? With the increase in voltage level, your current decreases. With the increase in voltage level, your current decreases. With the increase in voltage level, your current requirement decreases. Is it okay for the same kVA? Yes, sir. So by increasing the voltage level, now we can increase the voltage level to decrease the current, so that it will be possible to transmit with the thinner wires. Yes, of course, high voltage challenge will come into the picture, but we can hang it to more height. It means we can provide a more ground clearance to the transmission line. Is it okay? But yes, sir, it is possible. It is possible. Are you getting me? Yes, sir. Now please observe, we can't use this 440 kV. We can't use this 440 kV to our domestic loads. Like I have a fan. The rating of the fan is just 230 volts, sir, or 240 volts, sir. We have electric bulbs. That rating is just 220 or 230 volts, sir. Why we can't make a fan of 440 kV? Sir, if you are going to make a fan of 440 kV, then the size of the fan is bigger than our house. Yes, sir, because we need to provide insulation. If we are going to provide a insulation, correspond to the 440 kV, the size of the fan or the size of the equipments that we are using in the domestic as well as in the industrial purposes is very high. It will be not possible, sir. I can't make a fan bigger than my house. Yes. So what we do? We again need a transformer for a step down purpose. Again, we can decrease the voltage level with the help of the transformer. Is it okay? Yes, sir. Not only that, if you talk about your convenience, then you need to charge a mobile also. How you can charge a mobile? The voltage coming to your house is 230 volt. Yes, sir. And we need just 12 volt. And then we can use a rectifier to convert it into DC, or 5 volts to convert it into a DC by using rectifier, and then we can charge our mobile. So what we need there? We need a transformer there also. So transformer gives us a freedom. Transformer gave us a freedom to design any voltage level devices. You can easily operate that device on your desired level with the help of transformer. The entire distribution system is possible. The entire distribution system and transmission system is possible because of the transformers. So they are very essential part. Also, we need to reduce the current level, because if I am going to reduce the current level, I square R loss is also reducing. So I don't want to generate a to generate a 12 megawatt or a 200 megawatt, and just after it reaches to the load, if the current level is very high, it may be possible that entire power is going to be dissipated in the form of heat, I square R loss. So we don't want that. We have to reduce the current level during the transmission. That is only possible with the help of transformer. So now you know why transformers are so important for us. Is it okay? Yes, sir. Let me show you a complete power flow in our distribution and transmission system. Please observe here, I have represented a power station here. Yes, sir. So this power station may be of 200 MVA, maybe of 200 MVA and 11 kV. After generating this power, we need a power transformer. We need a power transformer. What a power transformer did? Sir, it is going to step up the voltage to a very high voltage level. Now, at a very high voltage level, let us suppose this is 11 kV, and now I am going to step up to 440 kV. Now at 440 kV, this transmission is going to done. After a transmission substation, it is again going to be changed from 440 to 66 kV. Is it okay? Yes, sir. Then again at the distribution substation, it is going to change from 66 kV to 11 kV or 6.6 kV. Is it okay? Yes, sir. So 11 kV or 6.6 kV. This 6.6 kV is directly transmitted to the industrial areas, because our industrial machines are a high voltage machines. Generally, induction machine can be designed up to 6.6 kV. So this voltage is transmitted directly to the industries. For domestic, again we need one more distribution transformer, and this distribution transformer is going to change the voltage level from 6.6 kV to 440 volt. All of you are already aware with the wires coming outside of your house. The three wires which are going just adjacent to your house are of 440 volts. 440 volts. This is a line to line voltage. Line to line voltage is 440 volts. When we talk about phase voltage, then it will be 440 by root 3. So it is just 254 volts around. Of course, there will be some drops occurs in the transmission line. So that is why in our houses the voltage appeared to be nearby 220 to 230 volts. Is it okay? Hoping now you are aware why transformers are so much important for us, because they give us a freedom to design our equipment as per requirement. As per requirement, you can design a transformer for power transformer to a small instrument transformer. Is it okay? Now let us discuss about the transformer. From here now onward you have to write. So write down transformers. First heading, write down transformers. You need to write it by your own. Okay, you have to make your notes. It's a prime requirement in order to understand this subject and all the concepts. Write down. Transformer is a static device. Transformer is a static device that transfers. Transformer is a static device that transfers electrical energy from one electrical circuit to another electrical circuit through magnetic fields without change in frequency. Without change in frequency. Okay. So I'm hoping you are wanting to know why without change in frequency. It's a very important term. Without change in frequency. Later on the operation, I'm going to explain it. Okay. Next, write down uses of transformer. Please write down uses of transformer. Uses of transformer. Uses of transformer. First point, already we have observed, to get the desired voltage level. Yes, sir. So first point, to step up or step down voltage levels. To step up or step down voltage levels. To step up or step down voltage levels. Next point. In electronic control circuit, transformers are used for impedance matching. Transformers are used for impedance matching, so that maximum power will be transferred from source to load. Maximum power will be transferred from source to load. You have already represented that power is going to be transmitted from here. So when we are going to reduce the voltage, then current is going to increase. Yes, of course. But that current is not only coming to your house. The current is distributed into the multiple different houses as well as different industrial loads. Is it okay? Yes, sir. So the thickness of wire is not needed to be very high. If we have to flow a 100 ampere current in a one wire, then thickness is high. If we have to flow a current of 100 ampere in 10 different wires, then sir, it is going to be 10 ampere only. Is it okay? Yes. It is not only for your house, na? So when we are going to reduce the voltage level, accordingly we are going to distribute in number of different houses also. Okay, great. Now please observe the fourth point, that is for isolating DC. For isolating DC, while it permits the flow of AC. For isolating DC, while it permits the flow of AC. So always remember, transformer cannot pass DC. If we have a AC component along with a DC component, then DC components are stopped at the input side of the transformer. Is it okay? Transformer can only and only work on AC. It can't work on DC. Is it okay? Yes, sir. Now, last one. Now, I'm hoping you are aware with the power electronics. So, in power electronics, transformers are used for gate pulse triggering. In power electronics, transformers are used for gate pulse triggering. I'm hoping already you are aware with this because you have completed your power electronics just before this. Okay, great, sir. Firing circuit. Yes, great. So transformers are used for gate pulse triggering in power electronics. So these are some major uses of the transformer that you need to know. Noted? Have you noted this? Great, sir. If you want that I will show a previous slide, just write PS. So it means previous slide. I will get that information you need, a previous slide. Great. Now come to the types of transformer. So in your books, transformers are divided in these different groups. But in actual practice, whenever if anyone asks you in an interview, how many types of transformers are there? Just say 3 types of transformers are there. First one is your instrument transformer. Second one is your distribution transformer. And the third one is your power transformer. So transformers are categorized only in 3 different groups: power transformer, distribution transformer, and instrument transformer. Okay, in books, it will be different. It will be differentiated in the format of types, in the format of connections, in the format of frequency. Okay, so I am representing here types of transformer. As per construction, transformers can be a shell type or a core type. Construction wise, transformers can be a shell type or core type. Okay? Yes, sir. Connection wise, phase wise, transformers can be a single phase or a three phase transformers. Transformers can be a single phase or three phase transformers. Then special transformer connections, that is auto transformer and Scott connection. Also open delta connection. So these are the special connections of the transformer. Then frequency wise, transformers can be a normal operating frequency transformer or high operating frequency transformers. High frequency transformers or pulse transformers finds a wide application in digital applications and in digital computers. Also they are used in the digital transmission systems. Okay, great, sir. So we have these types of transformer. Whenever anyone asks you in interview, sir, how many types of transformers, just say 3 types: power transformer, distribution transformer, and instrument transformer. Later on, let them ask, then you can say construction wise they are 2 and so on. Is it okay? Great. Noted? Yes, sir. So this is a little introduction about the transformer, hoping you are aware with all these terminologies. Now come to the some basic magnetic circuit parameters. In order to understand the transformer and the electrical machine, we need to know some basic terminologies. So just I am going to introduce you. Already you have studied these terminologies in your intermediate, your 12th class. But again, I am going to introduce some of them which is highly needed in this subject. Okay. So first one is permeability. Write down permeability. Write down permeability. The term permeability means, what is permeability, sir? It is the ability of the material to get magnetized. It is the ability of the material to get magnetized. Is it okay? Yes, sir. It is the ability of the material to get magnetized. In other words, it is the ability of the material to allow magnetic line of forces pass through it. It is the ability of the material to allow magnetic line of forces to pass through it. Yes, sir. Now please observe. Permeability is represented by the symbol mu. Permeability, I am going to represent it by the symbol mu, and mu is equals to mu naught into mu r, where mu naught is called as permeability of free space. Permeability of free space, and its value is 4 pi into 10 to the power of minus 7 Henry per meter. Is it okay? Yes, sir. Mu r is representing relative permeability. Mu r is representing relative permeability. Okay? Yes, sir. I am hoping you are aware with the term permeability. No, sir, we are not aware with the term permeability. Can you show more? Yes. Later on in this same lecture, I am going to relate electrical conductor and magnetic system. Okay. So then you can easily feel this permeability. Okay. For present, just write the term permeability. It is the ability of the material. It is the ability of the material to allow magnetic line of forces to pass through it. See, generally, when we talk about a free air relative permeability is very close to 1, but it is not 1. Air relative permeability is very close to 1, but it is not 1. When we talk about vacuum, then we can say relative permeability is 1. So generally mu naught is represented as a permeability in vacuum, but we say it like a free space. Free space means nearly vacuum. Okay. Now please observe here. Some basic concept of magnetic circuit. First I am going to show you MMF, magnetomotive force. Sir, what is magnetomotive force? What is magnetomotive force? It is similar to electromotive force. Like electromotive force is the reason behind the flow of current. Similarly, magnetomotive force is the reason behind the flow of magnetic line of forces. Okay? Yes, sir. It means you can say, sir, magnetomotive force MMF is responsible for the motion of magnetic flux, similar to EMF, like EMF is responsible for the motion of current. Is it okay? Yes, sir. Now please observe. We can represent MMF as N into I or H into L. Now what is this N into I? Please observe here. Let us suppose we have a material. Let us suppose we have a material here. Okay, it's a soft magnetic material. For a moment, assume that it is a soft magnetic material. And I'm going to just wound a wire over this. Okay, so I'm going to wound a wire over this in this fashion. Yes, sir. Now please observe here. Now please observe here. Sir, if the number of turns of this wire is N, let me show you only one. So if the number of turns are N, and current through the wire is I, if the number of turns are N and current through the wire is I, then it is going to create a magnetomotive force. That magnetomotive force can be represented as N into I, where N is the number of turns, and I is called as current through those turns. Current through turns. Is it okay? Yes, sir. It is also called as H into L. Now what is H? H is called as magnetic field intensity. It is represented by the symbol H. Magnetic field intensity. It is again similar to electric field intensity. Magnetic field intensity means driving force per unit length of the material. Means, sir, when we talk about the magnetic field intensity, then H is magnetomotive force per unit length of the material. So if we have this material having length, mean core length L, if we have material having mean core length L, okay, mean core length. If we have a material having mean core length L, then magnetomotive force per unit length of the material, is called magnetic field intensity. So magnetomotive force per unit length of the material can be represented as MMF upon L. Is it okay? Yes, sir. You can write it here as N into I by L. Is it okay? Yes, sir. Where L is called as a mean core length. So we can also represent H into L. Hoping up to this part everything is clear. Just a notation, just a name. Hoping you are now aware with just the name. Soon I am going to make this particular part to be field to you. Okay. Once we are going to be synchronized now, then once we are going to synchronize now, then it will be very easy to write down on your notes, and I am also synchronized with your speed. Noted. Great. Now come to the next term is magnetic flux. Now what is magnetic flux, sir? What is magnetic flux, sir? It is the measure of total number of field lines passing through an area. It is the total number of field lines passing through an area perpendicular to it. It is the measure of total number of magnetic lines. It is the measure of total number of lines. Just you can write up to this part. Okay. It is the measure of number of field lines. It is analogous to current. It is similar to electric current. in an electric circuit. Like electric current in an electric circuit, similarly in a magnetic circuit there will be a magnetic flux. Okay, great, sir. Now come to the magnetic flux density. So magnetic flux density is defined as magnetic flux per unit cross sectional area of the core, represented by the term B. It is represented by the term phi. Magnetic flux density is defined as flux per unit area of cross section of core. Now if you observe here, let us suppose this will be the area of cross section of core. So magnetic flux density is defined as number of magnetic line of forces per unit cross sectional area of the core. Is it okay? Great. Magnetic flux density B is defined as flux per unit area of cross section of core. Per unit area of cross section of core. Flux density is defined as flux per unit area of cross section of core. Yes, sir. Now please observe the term reluctance. Next term is reluctance. It is similar to resistance. We all know that resistance opposes the flow of current through them. In the same fashion, reluctance opposes the flow of flux through the material. Reluctance opposes the flow of flux through the material. If reluctance is high, we can say flux in the material is lower. If reluctance is low, we can say flux in the material is high. Is it okay? Yes, sir. So it is similar to resistance. In magnetic circuit, it is similar to resistance. Reluctance is defined as opposition offered to the magnetic flux by the magnetic circuit. Opposition offered to magnetic flux by the magnetic circuit. It is represented by RL, or sometimes in some books it will be represented as K. Okay, a small k, a little bit different symbol if you observe. It is similar to K and R, with this will be a little bit higher. Okay, there will be different notations in different books. In some books it will be represented by I also. So reluctance is defined as opposition offered to the magnetic flux by magnetic circuit. Okay, great, sir. Great, sir. Great, sir. Great, sir. Up to this part, I am hoping everything is clear. Now please see how we write a reluctance. The term reluctance is equals to L upon mu into A, where L is the mean core length, mu is the permeability, and A is area of cross section. Sir, from where you have represented this term, please see. Please see. Magnetic flux is similar to current, and magnetic flux is defined as MMF upon reluctance. Yes, sir. MMF upon reluctance. And we can represent it as Ni by reluctance. Is it okay? Yes, sir. So Ni by reluctance. We can also represent it in the way Ni by reluctance. Is it okay? Yes, sir. Please write one more point I have missed here, that B is also mu into H. B is also mu into H. B is also mu into H. Soon I am going to define this. B is also mu into H. Okay. Yes, sir. Now please observe here. You can write, sir. Flux is equals to Ni by reluctance. Yes, sir. Further, we can represent phi as B into A. So B is mu into H into A, and H is represented as Ni by L into A. So you can represent it as Ni by mu upon L into A. That we can call it as We can call it as MMF upon reluctance. MMF upon reluctance. Is it okay? Yes, sir. These are small terms that is highly needed for the subject. Please see. So I am going to tell you each and everything. I'm going to compare it with the electric circuit. Up to this point, everything is clear? Have you noted? Sir, we have noted, but still we are not feeling this. Still we are not feeling this. Okay, okay. So give me a small time. I'm going to show you. I'm going to show you the entire feeling, okay? I'm going to show you the entire feeling. First, tell me, first question, please write down question, first question. You can write just question number in your notebook because already you are going to download the PDF of the class. So you will have the questions. So just you can write the question number, okay? Or if you want to write the questions also, you can later on. You can later on write the questions. You can just leave a space for a question, okay? Now please observe question 1. In a figure shown below, the coil has 300 turns. So this coil has 300 turns, okay, sir, and carries a current of 2 ampere. Carries a current of 2 ampere. The path of the flux is shown by a dotted line. The path of the flux is shown by a dotted line, okay, sir. If the mean length of the core is 50 centimeter, if the mean length of the core is 50 centimeter, then the value of magnetic field intensity will be, kindly check. I have made a little bit mistake here. It's a L upon mu into A. L upon mu into A. AC in the studio is not working, so it will be quite difficult for me. Okay, so kindly update it in your notes. I have made a little bit of mistake here, that it is L upon mu into A. In my mind, I have represented correct, but during writing, I made a mistake. Kindly correct it. Okay, great. Come to the question. So, in the figure shown below, the coil has 300 turns and carries a current of 2 ampere. The path of the flux is shown by the dotted line. If the mean length of the core is 50 centimeter, then the value of magnetic field intensity will be. Magnitude of the magnetic field intensity will be. Magnitude of the magnetic field intensity will be. Great. Sir, we know about magnetic field intensity, that is H. Already, sir, you have represented H is equals to Ni by L. So, N is the number of turns, that is 300. Current given is 2 ampere and the mean length of the core is 50 centimeter. So, convert it into meters, okay? So, it will be 0.5 meter. Is it okay? Yes, sir. Now, this will be your field. Ampere turn per meter. You easily know about the units. Yes, sir. So this is the ampere turn per meter. Is it okay? Yes, sir. So that will be equals to 1200 ampere turn per meter. Great, sir. Option number A is correct. Great, sir. Option number A is correct. Now, hoping you have a better feeling of the MMF and the field now. Come to the next, comparison of electric circuit and magnetic circuit. I'm just trying to make this topic to be field, okay? Because you are aware with the electric circuit in a very good manner. So just I'm going to make this particular part easy for you. Please see. A comparison between electric circuit and magnetic circuit. Please write down. Comparison between electric and magnetic circuit. Just I'm trying to understand all the terminologies that I have introduced this before. Okay. Okay, sir. Actually, whenever I am saying when I am trying to understand, it means this is your internal voice. Yeah, great. Comparison of electric and magnetic circuit. So we have an electric circuit and a magnetic circuit here. Please observe. Let us suppose we have a conductor. And this conductor will have thickness and this conductor will have area of cross section A. This is a copper conductor. You can say a copper or aluminum conductor. The thickness is A. I'm going to apply a voltage V here, and the current flowing in this is, say, I. Okay? Yes, sir. The mean length of this conductor is L. The mean length of this conductor is L. Okay, sir. What happened, sir? Now the current start flowing, I. Yes, sir. Similarly, in a magnetic circuit, I'm just going to connect a voltage source here. That voltage source drives a current I through the number of turns N. Through the number of turns N. Okay. We have a soft magnetic material here. Let us suppose it's an iron ring, similar to the ring that I am holding in my this finger. Okay. Yes, sir. So this ring will have an area of cross section, say A. This ring will have an area of cross section, say A. Is it okay? Yes, sir. Now the current flowing I with a number of turns N. It will create a magnetomotive force. Yes, sir. Now please observe here. The length of this iron ring is equals to L. I'm just comparing. So we have a iron ring here and we have a copper ring here. In the copper ring, I'm going to connect a voltage source, so it will drive the current. And in this iron ring, I have wounded a wire with the N number of turns, and I'm going to supply a current I. Now, which electrical part you can say a circuit? How you can define an electric circuit? So the basic definition of electric circuit is closed path for the electric current is called electric circuit. Closed path for electric current is called electric circuit. It means, sir, if in any material, if we don't have a closed path for the current to flow, then that is not called as a circuit. Yes. A closed path for a current is defined as an electric circuit. Closed path for a current is defined as electric circuit. Is it okay? Yes, sir. Great. Similarly, closed path for the magnetic flux is defined as magnetic circuit. Is defined as magnetic circuit. Sir, closed path for the magnetic flux is defined as magnetic circuit. Closed path for magnetic flux is defined as magnetic circuit. So now you know what is electric circuit and what is magnetic circuit. Hoping this point is clear to you? Yes, sir. If a closed path is available for the current, then only you can define electric circuit. Similarly, when the closed path for the magnetic flux, then that path is defined as a magnetic circuit. Is it okay? Yes, sir. Now please observe. We have an area of cross section of this iron ring as A, mean length as L, L as a length of the conductor, and A as a area of cross section of the conductor. Current I is flowing, and I have applied a current I through N number of turns, so MMF will be there. So electric circuit and magnetic circuit. Further, please observe. I am just going to show you a electric circuit and a magnetic circuit. Electric circuit. In electric circuit, current is driven by the force called electromotive force. Current is driven by the force called electromotive force, and you can represent it by V volts. Yes, sir. V volts. Yes, sir. Let us suppose this to be the resistance R. In the magnetic circuit, flux is driven by the force called magnetomotive force. Magnetomotive force. And what is magnetomotive force? N into I, sir. N into I, sir. So we have MMF as a magnetomotive force which is driving flux, which is driving the flux phi, and opposition to the flux offered by an element called reluctance. Opposition to the flow of current offered by a component called resistance. Can I compare these two? Great. Now please observe. What is current I? I can be defined as driving force upon opposition. Driving force upon opposition. Yes, sir. Similarly, flux can be defined as driving force upon opposition. Opposition. Yes, sir. Great, sir. So you can say, sir, V by R in electric circuit, and in magnetic circuit you can say, sir, MMF N into I by reluctance. Is it okay? Is it okay? Yes, sir. Yes, sir. We are also aware with the term current density. What is current density? What is current density? Sir, current density is defined as I by A. It means current per unit area of cross section of wire. Current density can be defined as current per unit area of cross section of wire. Yes, sir. Current density can be defined as current per unit area of cross section of wire. Similarly, flux density can be defined as flux per unit area of cross section of material. Is it okay? Yes, sir. Area of cross section of iron. I am using this iron, so area of cross section of this iron. Is it okay? Great, sir. Now we have a complete feeling of magnetic flux density. Now we can clearly observe the current and flux, how you are relating. Is it okay? Great, sir. Up to this part, everything is clear? Sir, electric field intensity, E can be defined as driving force per unit length of the conductor. Driving force per unit length of the conductor. What is electric field intensity? Driving force per unit length of the conductor. Yes, sir. What is magnetic field intensity? Driving force. What is driving force in magnetic circuit? MMF. So MMF is going to drive the flux. So MMF upon L. Yani you can say, sir, magnetic field intensity per unit length, magnetomotive force per unit length of the conductor. So you can represent it as Ni by L. Is it okay? Now you have a better feeling. Yes, sir. Now please observe. Sir, what is the value of V? We can write V as I into R. In this circuit, we can write V as I into R. Yes, sir. Upon L. The same thing exists for the magnetic circuit also. You can write, sir, magnetic field intensity as Ni. Ni can be represented as MMF. MMF can be represented as, in terms of flux, it can be represented as flux into reluctance. Sir, already you have represented that flux is equals to MMF upon reluctance. MMF upon reluctance. So N into I can be represented as flux into reluctance upon L. Can I write in this way? Yes, sir. What is resistance, sir? In electric circuit, resistance is represented as R is equals to rho L by A, where L is the length of the conductor, mean length of the conductor, A is the area of cross section of conductor. Yes, sir. Similarly, you can represent phi by L. Reluctance can be represented as, sir, mu upon L into A. L upon mu into A. L upon mu into A. Yes, sir. You can represent in this way. So this L and L is going to be cancel out. In magnetic circuit also, the length, mean core length is going to be cancel out. Further, you can write E as I by A. So, sir, I can write rho into I by A. We all are aware with this, rho into J. E is equals to rho J, where what is rho? Resistivity of the material. Yes, sir. Similarly, you can write here also as H is equals to phi by A into 1 by mu. Is it okay? Yes, sir. You can write, sir, J is equals to sigma E, where sigma denotes ability of the material to conduct. Yes, sir. Now please observe here. You can write, sir, phi by A as flux density B. B is equals to mu into H. Now you have a great feeling related to this comparison. Is it okay? Now you can feel all the magnetic parameters. Sir, ability of the material to magnetize, ability of the material to conduct. Is it better? Is it better now? I need your answer. I need your answer. Do you have better feeling after this comparison? Each and every parameter now better, you have a better understanding of each and every parameter of magnetic circuit. There is one difference in magnetic circuit and electric circuit. See, in electric circuit, electrical isolation is possible. Electrical isolation is possible. However, in magnetic circuit, magnetic isolation is not possible. It is quite difficult. In order to have a magnetic isolation, we have to surround the magnetic fields by some conductor. Okay. And even if we are going to surround it by some conductor, there will be a high eddy current flows in the entire boundary. So the heating effect is going to be happen. So magnetic material cannot be isolate. You can't stop the magnetic line of forces to flow. However, in open air, current can't flow. Is it okay? Yes, sir. So this is the basic difference between the magnetic circuit and electric circuit. Up to this part, everything is clear? Great, sir. Let's see one question now. We have a one iron ring that I am holding in my finger. We have one iron ring. We have a one iron ring. This iron ring is of mild steel and the mean diameter is 20 centimeter. This is your second question. This is your second question. Okay. Yes, sir. We have an iron ring, steel, mild steel ring, and mean diameter is 20 centimeter. Cross-sectional area is 50 centimeter square. The relative permeability is 800. Relative permeability is 800. So its relative permeability 800 means its ability is 800 times than air or a vacuum to have magnetic line of forces. Great, sir. So now we have a better understanding of relative permeability also. Calculate reluctance of the ring. Calculate reluctance of the ring. And if I'm interested to create a flux of 1 milliweber, then you have to find the number of the current flowing through the 200 number of turns so that it can create a flux of 1 milliweber in the ring. So I am going to create a flux of 1 milliweber in this ring. Is it okay? Yes, sir. We have an iron ring. We have an iron ring. This is your iron ring. We have an iron ring here. Yes, sir. And we have an iron ring here. And the length of the diameter, mean diameter of this ring is, sir, mean diameter of this ring is 20 centimeter. Mean diameter of this ring is 20 centimeter. Yes, sir. This is your diameter. Diameter of the ring is 20 centimeter. It is given. Also, area of cross section of the ring is given to you. Area of cross section of the ring is 50 centimeter square. Its relative permeability is 800. Its relative permeability is 800. I have to produce a flux of 1 milliweber in this ring, and I am going to surround 200 number of turns over this ring. Is it okay? So we have to calculate current required to be flow through this ring as well as reluctance of the ring. It is Henry inverse, or also you can observe reluctance unit is Henry inverse, and also reluctance unit you can observe here. Please observe reluctance unit is, this is your MMF upon reluctance. So what is MMF? MMF upon flux. MMF is N into I by flux phi. So this is ampere turn per Weber. Is it okay? You can also represent the reluctance as ampere turn per Weber or Henry inverse. Henry inverse is also the unit of reluctance. Is it okay? How to calculate the reluctance? Sir, reluctance is defined as MMF upon flux, or you can say, sir, L upon mu into A. Reluctance can also be defined as L upon mu into A. So please move through the L upon mu into A. Now what is L? L is your diameter. If you know about the diameter, you can calculate the mean length. What is mean length? Sir, if we have a mean diameter, then circumference of this circle is 2 pi r, or you can say pi into d. This is your mean length of the core. So we have mean length of the core as pi into d. We have mean length of the core as pi into d. I think you have missed this d. And mu can be represented as mu naught into mu r into a. Is it okay? Yes, sir. So we have pi into diameter is 20. Diameter is 20 centimeter, means you have to convert it into meters because your mu naught is in Henry per meter square. So in Henry per meter, so you can write it here as 20 into 10 to the power of minus 2 upon mu naught is 4 pi into 10 to the power of minus 7 Henry per meter into 800 into area of cross section. Area of cross section is given to you as 50. Convert it into meters. So write it as 10 to the power minus 4 meter square. Now you can calculate the value of reluctance. Is it okay? Please observe, if the radius is known, then you have to use 2 pi. Otherwise, you have to use pi d. For electrical machine, I will suggest you to follow, if you have a MS, then you can follow 991 MS or 991 ES. See, we have to go through the number of numericals, and the numericals in books are very close to the real or actual practice machines. So they may have a different data which needs to be calculated faster through the calculator only. However, when the question is asked in GATE, they have framed the question always. We have observed it in the previous year also. They frame the question in such a manner that it can be easily solved by the on-screen calculator. So my suggestion is go through the calculator for the practice purpose, and once you are going to solve the number of questions on test series, then you can follow the on-screen calculator. On-screen calculator you can easily learn by going with 2 or 3 calculations only. Okay? Yes, sir. Sir, this will be equals to 220 into pi into 10 to the power of minus 2 divided by 4 pi into 10 to the power of minus 11, okay, into 50 into 800. So 125,000. Is it okay? Yes, sir. Ampere turn per Weber. Up to this part, everything is clear? Great, sir. Now also we need to calculate the current. I am interested to create a flux of 1 milliweber in the ring. So what current is needed? How the amount of current needed is, sir, flux is defined as MMF upon reluctance. Yes, sir. So what is MMF? N into I by reluctance, sir. N into I by reluctance, sir. And we have the value of flux. So flux into reluctance upon number of turns. 1 milliweber means 10 to the power of minus 3 into reluctance 000 by number of turns 200. So please find the value of current needed to set up the flux of 1 milliweber in the ring. Now you can create any amount of flux in any dimension of core. Is it okay? For any dimension of core, you can easily create a flux. You have a better understanding of this magnetic circuit. It is very similar, like if you have known to be the resistance and the voltage, you can easily find the value of current. So in the very similar way, we can find the current also. Is it okay? Now come to the next part, that is magnet. Next part, that is magnet. You all are aware with the term magnet. Yes, sir. From our childhood, we are playing with a magnet. That is why we have chosen electrical engineering as a profession. Huh? Yes, sir. So, magnet. You are aware with the term magnet. I'm just going to recall you. Sir, A magnet will have two poles. A magnet will have two poles called North Pole and South Pole. Called North Pole and South Pole. And sir, a magnetic material shows this behavior because of its magnetic dipoles. Magnetic dipoles are formed because of spinning of unpaired electrons around the nucleus or around its own orbit. Yes, sir. So because of spinning of unpaired electrons, there will be a small magnet formed. The atom itself acts as a magnet, and that is going to be a dipole. These dipoles are represented by a circular loop with a arrow. The arrow head is representing direction of field. Okay? Yes, sir. So in a magnetic material, these dipoles are aligned in one direction, and they are responsible for making this material to behave like a magnetic material. Because these dipoles are the smallest magnet, and the arrow tip is north and the arrow tail is south. Is it okay? Yes, sir. These dipoles are going to create a magnetic field, and that magnetic field comes out from the material called north and going inside the material again called south pole. Is it okay? Yes, sir. So the north terminal is that terminal from where magnetic line of forces are going away. From where magnetic line of forces are going away from the material. And south is that pole from where magnetic line of forces are again coming back to the material. Is it okay? Yes, sir. How we decide the north and south, and can we see these magnetic line of forces? Yes, it's possible. Even in your ninth standard, you have done this experiment. One magnet is put onto the plain paper, white paper, and then a powder of iron is spread around the magnet. All the magnetic line of forces are going to be visible to you. Yes, sir. But it's difficult to mark north and south. So for marking north and south, we take Earth north and south. Our Earth will have an electric field and a magnetic field, north and south. Yes, sir. So based on that north and south, our magnet polarity can be marked. Is it okay? Yes, sir. Now please observe. If we have a small iron piece, if we have a small iron piece, then this iron is not acting as a magnet. Yes, sir. This iron is not acting as a magnet. Yes, sir. But this iron material will have dipoles. If we have a iron material, then it will have dipoles, but it is not acting as a magnet. The reason behind that is the dipoles are randomly oriented. So net magnetization in the material is 0. It is not behaving as a magnet because all small dipoles are randomly oriented. Is it okay? Yes, sir. When I am going to put it close to the magnet, what happened? Sir, when you are going to put this iron close to the magnet, it is going to be attracted towards the magnet. When you are going to put it close to the magnet, it is going to be attracted by the magnet. Why, sir? Because magnetic line of forces always try to flow through the low reluctance path. Yes, sir. And sir, this iron will have dipoles. Dipoles can provide path to the magnetic line of forces. So these magnetic line of forces try to flow through the low reluctance path, and they found a path through this dipole. So they try to make these dipoles to be aligned in the direction of magnetic field. Once they are going to be aligned in the direction of magnetic field, this iron piece also becomes the part of the magnet. Is it okay? Yes, sir. So we know why a magnet attracts soft iron. Why a magnet attracts soft iron? Yes, sir. Why a magnet attracts soft iron? But when we put a conductor, nearby the magnet, what happens? Sir, conductor always repel magnetic line of forces. So when we try to put a conductor nearby magnet, it is not going to be attached, because in conductors, dipoles are going to be aligned opposite to the magnetic line of forces. Dipoles always align opposite to the magnetic line of forces. Is it okay? In conductive materials. In magnetic materials, dipoles align in the direction of magnetic field. Yes, sir. Let us suppose we have another magnet. Suppose we have another magnet, and this magnet will have a polarity as north and south. So it means this magnet will have a magnetic line of forces coming in this fashion. Yes, sir. That part is said to be north, from where magnetic line of forces are going away from the material, and that part is said to be south, from where magnetic line of forces again entering into the material. Okay, sir. Now please observe here. If we try to shift this magnet towards the north, what happens, sir? It will feel a repulsive force. Why? Because of the magnetic line of forces. Is it okay? Yes, sir. Why? Because of this magnetic line of forces. However, if I am going to put this north nearby this south, what happened? Sir, it is going to be attracted. Yes, sir. Is it okay? Yes, sir. So we know about the attractive principle and repulsive principle through the magnetic line of forces in the permanent magnet. Our machines will use our machines are going to use magnet. Every machine is going to work on magnet only. Every machine is going to work on magnet only. Even a rotating machine also are going to work on magnet only. Why? Sir, let us suppose we have a permanent magnet here. Okay. And sir, we have a magnet here. And this magnet is hinged. This magnet is hinged. So what happens, sir? If this magnet is hinged, sir, it will remain its axis but try to align towards the north. Yes, sir. If I have another magnet here, which will have a polarity of north here, then what happened? The south will be attracted towards that magnet. Yes, sir. And rotation is possible. Based on this principle only, the entire rotating electrical machines are going to work. Is it okay? Yes, sir. Great. Up to this part, everything is clear? Hoping it's basic thing. You have a better understanding of magnets. You have started playing with the magnets right from the class 6th. So you have a better understanding of permanent magnet. But the difficulty is that in a permanent magnet, we can't change the magnetic field intensity. We can't change the magnetic field intensity. That is mmf per unit length in the conductor. And we want to change it. For operating our electrical machine, we need to change the magnetic fields. Okay, the strength of the magnetic field. So for that, we will use electromagnet. Now, how the electromagnets are formed? Before going to the electromagnets, please observe right-hand curl rule. Okay. This is most important part of the entire electrical machine. Once you are able to understand right-hand curl rule, then everything will be very easy for me to show you. Okay. Please observe right-hand curl rule. If we have a wire, and this wire is carrying a current I, then it will create a magnetic field, because magnetic isolation is not possible. So every current carrying conductor is producing a magnetic field. Is it okay? Yes, sir. So we have a wire and it carries a current I. Now, in order to understand the direction of magnetic field produced by the current flowing through the wire, we will use a right-hand curl rule. For that, it is very simple. You have to put your right-hand thumb in the direction of current. And fold your four fingers. This is your right-hand curl. The direction represented by this right-hand curl is called the direction of magnetic field. Is it okay? Yes, sir. So if we have a current carrying conductor, it is going to create a magnetic field, and the direction of magnetic field can be found by the right-hand curl rule, where this thumb is representing the direction of current and the right-hand curl is represented by this. The magnetic field direction can be represented by this right-hand curl. It can be clearly observed that magnetic line of forces are coming towards the observer from the upper portion. Yes, sir. So it can be represented by the dot. I am an observer. Magnetic line of forces are coming towards me. So that portion is represented by the dot. And magnetic line of forces going away from the observer is called dot. Is it okay? Yes, sir. So magnetic field, direction of magnetic field can be marked in terms of dot and cross. Is it okay? If the current flows in the direction of right hand thumb, then right hand curl is the direction of magnetic field. It can be clearly observed that the magnetic line of forces are coming towards the observer, represented by dot, going away from the observer, represented by cross. We all know that the material portion from where magnetic line of forces are coming out is said to be north, and from where magnetic line of forces are going away is called south. Coming out is called north, and going towards the material is called south. So we can easily mark the north and south. One may ask, sir, what happened if I am going to see this wire behind the board? So if you are going behind the board, then definitely you will found different north and south. So that is why I have added the word towards the observer and away from the observer. Is it okay? Again, suppose we have a wire, and this wire is carrying a current. This wire is carrying a current in this direction. This wire is carrying a current in this direction, which will have a magnetic line of forces towards the observer, and which will have magnetic line of forces away from the observer in terms of A and B. Please mark A and B in terms of dot and cross. Use right hand curl rule. In right hand curl rule, thumb is representing the direction of current. If any wire, it will create a magnetic field. If any current carrying wire, it will create a magnetic field. The direction of magnetic field can be easily be found by using right hand curl rule. Thumb is representing the direction of current, and curl is representing the direction of field. So in this curl, which one is dot and which one is cross? A is cross and B is dot. So magnetic line of forces are appearing that it is going away from the observer in A and coming towards the observer in B. Is it okay? Yes, sir. So we can mark this as south, this as north. You can feel if we have two wires carrying current in opposite direction, then they will feel repulsive force. If we have two wires placed near to each other and they carry current in opposite direction, they will feel repulsive force. Is it okay? Yes, sir. Further, again, please observe again. Suppose we have a wire. We have a wire here, and this wire carries a current in this direction. This wire carries a current in this direction. Please mark in terms of dot and cross in C and D. Please mark dot and cross in terms of C and D. Please mark dot and cross in terms of C and D. Yes, sir. If the current is flowing in this way, this is same. That is dot, cross and dot. Is it okay? By the right hand curl rule. So, sir, this is going to be the south and this is going to be the north. It concludes that if we have two wire carrying current in same direction and they are placed near to each other, they feel attractive force. They feel attractive force. They feel attractive force. Great, sir. So based on this important thing, I am just going to write a thumb. This is a right hand thumb and right hand curl. Okay? Yes, sir. Right hand curl. So one can say, sir, if the current flows in the direction of right hand thumb, then right hand curl is represent the direction of magnetic field. Right hand curl represent the direction of magnetic field. Is it okay? Yes, sir. Great, sir. Now please observe. Suppose we have a iron core here, and over this iron core I am going to provide a insulation. Here. This is a insulation. So onto the iron core I am going to provide an insulation. Now I am going to provide an insulation here. So this insulation I am representing by a pink color line. Is it okay? We have a white color core. over which I have represented a pink color insulation. Over that, I'm going to wound a wire. Okay. Yes, sir. Suppose I am going to wound a wire in this way. Please try to feel it. It is like that. Okay. Yes, sir. So wire is wounded in this manner. Is it okay? Yes, sir. And suppose I'm giving a current I. So this current I is going to flow in the wire in this manner. Is it okay? Yes, sir. Now please observe. Now please observe. You can say, sir, we know if there will be a current carrying wire, it will create a magnetic field. We know if there will be a current carrying wire, it will create a magnetic field. Yes, sir. So let us suppose only that portion of the wire which I have highlighted here. Only that portion of the wire which I have highlighted here. Okay. Yes, sir. So if this wire, it will create a magnetic field, and we know about the right hand curl rule. So if the current flowing in the wire in this fashion, it will create a magnetic field like this. Yes, sir. So it means it will create this as a dot and this as a cross. Again, this as a dot, this as a cross, this as a dot, cross, dot, cross, dot, cross. Is it okay? Yes, sir. Now, we know, sir, how to mark north and south. So, by observing this, you can mark this to be the north and south, 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 this to be the north and south. It looks like a small magnets are going to be connected. So the entire this is going to act as a magnet. And what is the polarity? Sir, the polarity is this terminal is going to act as a north, this terminal is going to act as a north, and this terminal is going to act as a south. Is it okay? Yes, sir. Now I'm going to make it a little bit easier. Whenever you have a coil, because this is a coil, so I have provided an insulation between the iron and the coil. Otherwise, what happened? These coils are shorted. If the coils are shorted, then instead of having coil, it will become a simple conductor. Is it okay? Yes, sir. So that is why I have provided an insulation adjacent to the core. Now, we have a wire in the format of coil. Whenever we have a coil, we can find the magnetic field by using right hand curl rule. If the current flows in a coil in the direction of right hand curl, if the current flows in a coil in the direction of right hand curl, then thumb represent the direction of magnetic field. If the current flows in a coil in a direction of right hand curl, then thumb represent direction of magnetic field. So this magnet will have a magnetic field in this manner. Is it okay? Inside the material, magnetic line of forces travel south to north. Outside of the material, magnetic line of forces travel north to south. Always remember this. Is it okay? Yes, sir. Again, please observe. Suppose we have, again observe. Suppose we have a iron piece, and over this iron piece I am going to wound a wire. Yes, sir. Suppose we have a iron piece, and over the iron piece I am going to wound a wire. Yes, sir. Just providing a simple DC supply to it. Yes, sir. Just providing a simple DC supply to it. Yes, sir. Can you mark the polarity of north and south in terms of AB and in terms of CD? This is what we call electromagnet. We all are aware, if the current flows in a coil, in the direction of right hand curl, then thumb is representing the direction of north, or the magnetic field, direction of magnetic field. Yes, sir. So it can be clearly observed here, sir, the current is flowing in this manner. Current is flowing in the direction of right hand curl. If current in a coil flows in the direction of right hand curl, then thumb will represent the direction of magnetic field. So B is north and A is south. Is it okay? Similarly in this one. So the current is flowing here in this manner. Yes, sir. So what is the polarity? Sir, as per the right hand curl rule, this is going to be the north and this is going to be the south. Is it okay? Yes, sir. So now you can mark the polarity of electromagnet, and also you can make the polarity of electromagnet as per your choice. Yes, sir. You can make the electromagnet as per your choice. Yes, sir. So, sir, second point of this right hand curl rule, we can represent here as, if the current flows in the direction of right hand curl, then thumb represent the direction of magnetic field. Flux field can be a DC or it can be a AC. If you are going to supply a DC, then always this terminal will remain north and this terminal will remain south till the current flows. In case if you are going to supply AC, then what happened? Half cycle this current flows, then half cycle this current flows. Is it okay? Is it okay? Yes, sir. So it means polarity of magnet change in every half cycle. Is it okay? Till the current DC flows, it will create a DC field. When the current AC flows, it will create a AC field. We have both machine, AC machine as well as DC machine. And in both we need to create a flux. Is it okay? Great, sir. So that is why I have represented these two. One more very important thing. If you observe one more figure, I am going to show you one more figure. Please observe here. Suppose we have this same magnet. We have the same material. Over the material, I am going to wound the wire. Same wire, but in a different fashion. If you observe, the two wires will have different fashion. Yes, sir. This wire is wounded in a anti-clockwise manner, and now I am going to wound the wire in a clockwise manner. Okay? Yes, sir. Same current is supplied to it. Same current is supplied to it in the same direction. Yes, sir. What happened? Sir, current will going to flow in this manner. Yes, sir. So with this direction of current, what is the polarity of magnet? Sir, polarity of magnet will become north and south. It can be clearly observed for the same winding, if the direction of current reverses, field reverses, and for the same current, if the way of winding changes, then also field changes. So field depends upon two different things. Polarity of the electromagnet depends upon two different things. First is direction of current, and second is the way of winding. That is very important. The way of winding. L di by dt is 0 and constant current. No current. No. About the inductor, I am just saying about the DC flux. Yeah, of course, DC flux will exist. If you are asking about the inductance, sir, there will be no inductance for the DC. The flux is existing, but the flux is not alternating in nature. Okay? I have supplied a DC. In a DC machine, we have DC fields. In a AC machine, we have AC fields. So I have supplied a DC, then always the polarity will remain same. There will be no change in the polarity of the magnet. If you are going to supply a AC here, then in every half cycle, polarity of magnet changes. Is it okay? Let me show you one more. Suppose we have a iron piece which is arranged in this way. I need your attention. Suppose we have an iron piece arranged in this way. So this is your iron piece arranged in this way. Suppose we have an iron piece arranged in this way. Okay, we have an iron piece, the color is also like iron only. So we have an iron piece arranged in this way, and I am going to wound a wire over it. I am going to wound a wire over it, and that wire is wounded in this fashion. Okay. And then I am going to apply a DC over this wire. Can you tell me what is the polarity of A terminal and B terminal, which is going to act as a north and which is going to act as a south? Can you tell me which is going to act as a north and which is going to act as a south? Which is going to act as a north and which is going to act as a south? Can you tell me which one is going to act as a north and which one is going to act as a south? The current flows in this manner. The current flows in this manner. So if you observe, sir, current flows in this manner. So magnetic line of forces are coming out from the material from here. Yes, sir. And it is again going back to the material here. So magnetic line of forces are going to complete their path in this way. Magnetic line of forces are going to complete their path in this way. Please see. Magnetic line of forces are going to complete their path in this way. Yes, sir. Magnetic line of forces are going to complete their path in this way. In this way. If I am going to show the entire magnetic line of forces by two magnetic line of forces, they are going to complete their path in this way. Now please tell me which one is north and which one is south. Which one is north and which one is south? Sir, magnetic line of forces are going to pass through this in this way. Right hand curl. Right hand curl. So this is going to act as a north. This is going to act as a north and this is going to act as a south. So our DC machine will have a field like this. Yes, sir. Again, please observe one more. Suppose we have a conductors carrying current in this way. We have a conductor carrying current in this way. Assume it like it is coming out to the board in a cylindrical manner. Is it okay? Yes, sir. These are the wires. These are the wires. And they are going to carry a current in this way. So, I have a material. This one. Okay. Please tell me what is the polarity of north and south and how to find. We have a terminal A and we have a terminal B. How to find the magnetic field? Sir, the current flows in the direction of thumb. If we are considering a conductor, then current flowing in a conductor in the direction of thumb. Then right hand curl is the direction of magnetic field. So if right hand curl is the direction of magnetic field, it will going to create a magnetic field in this manner. It will create a magnetic field to complete its path in this manner. Please observe. Instead of showing with every individual conductor, I am just representing here. So it will create a magnetic field in this manner. And these conductors are going to create a magnetic field in this manner. Thumb is the direction of current and right hand curl is the direction of magnetic field. So magnetic line of forces are going to complete their path in this manner. So which one is north and which one is south? Tell me which one is north and which one is south. Sir, here magnetic line of forces are coming out from here. So this is north and this is south. Is there any issue with this? Please let me know. This is what we call rotor of a synchronous machine. Is it okay? Hoping you have enjoyed this class. Okay.